we have an invited speaker from BRIN, National Research and Innovation Agency. So this is Christine Ratri, Tribu Tani, Satya Stuningsi, Muhammad Khalid, and Adam Februari. Adam. Okay, Ibu. Oh, okay. We are waiting for the technical issues. So from BRIN, they will be presenting about the electrochemical characterizations of green solid polymer electrolyte based on PVA cytosan blend. So we have Miss Tri Utami. Also, we want to thank you for the Thermo Fisher Scientific as the gold sponsor for our event, international conference on advanced material and technology 2022, and also all the sponsors from Vector, Trinseo, and also the LSP Kimia industry, and also APNI as our partner in collaborating for the ICAMT 2022 and also the training of trainers. Okay. So Miss Tri Utami.
Christine.
Oh, Miss. Oh, sorry. Miss Christine. Okay. So the time is yours.
Thank you, Professor Evi and National Battery Research Institute of Indonesia for allowing me to present our research. My name is Christine. I'm a student in Universitas Indonesia from the Department of Metallurgy and Materials, and I work at the Battery Research Center Group of Research Center of Advanced Material BRIN. And I will present now our research about electrochemical characterizations of green solid polymer electrolyte based on PVN cytosan blend. This is the annual sales and sales projection of electric vehicle that is expected to increase up to 2040. We can see that it will be steadily increasing, as we also see that now in Indonesia we already have readily available electric vehicles to buy. And this is, of course, the projection of lithium-ion battery that it will be used for the future that will be dominated by electric vehicles. Of the manufacturing cost in battery production, we break down the cost and we can see that, we can see that material dominates the manufacturing cost, and of the materials cost, we can break them down. And the largest material cost is of the cathode, separator, and electrolyte. This is the scheme of lithium-ion battery. As we can see, we have two sides of electrode, which is anode and cathode. And we also have electrolyte and separator. The electrolyte is made of the commercial one. We have liquid electrolyte, which is comprised of lithium salt dissolved in carbonate solvent. And the separator is made of cell guard separator, which is a 3-layer polypropylene, polyethylene, and polypropylene. The disadvantage of the commercial battery is that it contains liquid electrolyte, which is prone to leakage, which could result in fire. And also the salt that being used, lithium hexafluorophosphate or LiPF6, is very detrimental to electrodes, so it can be harmful for the lifetime of battery. So how can leakage and fire turns into a fatal accident? First, the electrolyte salt decomposed at 50 degrees C. So we should remember that high operation of battery can result to a very fatal accident because it produces toxic gases, and the separator melts at 130 degrees C, producing oxygen, which we don't want, because this oxygen, if it reacts with the solvent from the liquid electrolyte, it would create exotherm reactions, and this exotherm reaction, of course, will produce heat, and the unescaped heat would result in chain reactions, and this can result in temperature increasing up to over than 200 degrees C. We can see at the right side, the upper side is the pristine lithium-ion cell, and the bottom one is after the thermal runaway, after it catch fire. So what is the solution? We have seen many research about solid-state battery to overcome this issue, which is the combo electrolyte and separator. On the right side of the picture, we can see that we have no more liquid electrolyte. So we replace them with the membrane solid electrolyte. But it still have a relatively low conductivity compared to the conventional liquid electrolyte. So the main highlight of the solid electrolyte is, of course, the polymer host, because it is the main membrane. And the requirements is the first, it has to be freestanding because it has to be flexible. We have lots of form of gadgets. It has to be formed in many shapes. It has to also be soluble in most solvents, and also it has to have low crystallinity to improve its conductivity. And the last one, for industrial scale, it should be low cost and scalable. So we move to holistic overview of a fabrication of sustainable membrane. We have to start with the green raw materials first, and then we move to greener fabrication methods, and then we have to think more about less waste, and then we also have to use low toxicity chemicals, so we can minimize the potential of toxic and safety. The first step towards the green materials is to start from nature. We can see the 4 quadrants here, where we can see the bio-based and fossil-based, and on the horizontal axis is the biodegradable plastic and non-biodegradable plastic. Of course, we want to see the upper right quadrant, which is the bio-based and biodegradable. And for this, we use the polymer host, polyphenol alcohol, and chitosan, because chitosan is abundant and it is a waste. So we can actually process the waste into something that are much more useful. So the PV and chitosan both are non-toxic and biodegradable. It is highly soluble in water. It can be dissolved easily in water or in just 1% of acetic acid. And it will be minimizing use of toxic and flammable solvent that is currently used, such as dimethyl acetamide, DMAC, or NMP, or DMF. And lastly, it has low crystallinity compared to commercial separator. The electrolyte salt, we use lithium bisoxalatum borate, which is thermally stable up to 70 degrees C. It is compatible with most electrode materials, and it is stable at high voltage. This is a overview of ion transport mechanism in polymer electrolyte. A lithium ion moves between amorphous and crystalline segments of the polymer using segmental motion as well as ion hopping. So to easy to make ion mobility is easier. We facilitate that using plasticizer because plasticizer works by relaxing polymer chain and lowering crystallinity, therefore assisting segmental ions, segmental motion and promoting ion movement. And glycerol is green because it can be obtained from plant and animal source. Here we explain our experimental method where we dissolve PVA and ketosan in the ionized water and we turn it into a homogeneous slurry and we cast it on a petri dish and we dry it and in a desiccator. At the right side, we can see that PVA alone result in transparent membrane. PVA with Libop salt result in opaque white membrane, but it is slightly inhomogeneous. But after we add ketosan and glycerol, it turns into more flexible membrane and more homogeneous. This is the material characterization. So for the electrochemical characterization, we use temperature and humidity chamber for temperature variations. And we use potentiostat to measure the impedance and to further calculate the ionic conductivity. We use the coin cell CR2032 and we put our electrode membrane sandwiched between two stainless steel plates. Using this formula, we calculate the ionic conductivity. So the left side is the Nyquist plot where we plot our impedance obtained from the potentiostat measurement. And we can see that this is the variation of salt concentration. So we have 10% salt, 20% salt, 30% salt, and at the most right side, we use a cell guard separator, which resembles commercial battery. We can see that 10% salt concentration gives the best ionic conductivity, even better than the commercial battery that used commercial separator. And then this is the plot of the ionic conductivity when we elevate the temperature and calculate the impedance. We can see on the graph on the right that from room temperature, the ionic conductivity is 3.7 to the 10 to the power of -5, and it decreases as we increase the temperature. And this is at first confuse us as to why, because it is contrast to typical experiment, Arrhenius law. We can see on the formula that usually ionic conductivity increase with the increasing temperature, but here in our experiment, we see that it is steadily decreasing. So we are looking for the answer by first analyzing the dielectric loss. We see that for ideal capacitor, we have 90-degree angle as we move the voltage. We have the current, but with a lossy dielectric, we have Tangen delta, which can be defined as the dielectric loss. So at the formula here, the epsilon prime and epsilon double prime, we translate the impedance we get from the measurement into the dielectric constant and dielectric loss. And this is what we have from the analysis of dielectric loss from the frequency and the epsilon double prime or dielectric loss. We see that the electric loss basically is the energy wasted into heat. So it cannot be stored as more energy. And here we can see the trend that the electric loss is increased upon heating. This shouldn't be happening, but at high frequency, charge accumulation occurred at the interface because the ion is staying at the bulk. It does not move, and it is lessening polarization. So less ions is mobile between two electrodes, and thereby it is increasing the dielectric loss. And we further analyze it using loss tangent. And this is also the indication of how material is efficient or inefficient as dielectric materials. And we can see here at the curve that from the room temperature to 40, 50, 60, and 70, the curve is steadily shifting and even increasing. The higher Tangen delta, which is conversely proportional to the electric loss, was observed with increasing temperature. This is also confirmed by the impedance before at the Nyquist plot and ionic conductivity and the dielectric loss plot. So it is confirmed by previous analysis. And shifting and steadily increasing peaks means high relaxation time because the long migration of the ions causing lower ionic conductivity because it is taking too long to move. So what is causing this? It is the moisture-induced plasticization. So we know that glycerol is very hygroscopic. And glycerol in the ambient moisture, it traps water molecules from ambient moisture. And in enclosed chamber, increase in temperature is inversely proportional to relative humidity. So elevating temperature or heating results in less moisture. So deplasticizing effect, and less plasticizing means lower ionic mobility and lower ionic conductivity. So in conclusion, we have fabricated solid polymer electrolyte using biodegradable materials via solution cast technique. The first finding we have found is to high salt concentration might result in aggregation, which hindered ionic mobility. And we also find out that we can actually make a solid polymer electrolyte in all solid state battery that is better than commercial battery with liquid electrolyte. And the third finding we find here is the membrane conductivity decreased with elevating temperature due to plasticizing effect. And despite unusual trend towards the typical Arrhenius law, high room temperature conductivity is advantageous for our daily operation because we do not operate battery at high or elevated temperature, of course. But further observation is required to analyze the effect of ambient moisture on overall performance of battery. So acknowledgement, we would like to thank the Hibah Putih Pascasarjana Universitas Indonesia and also LPDP Beasiswa Pendidikan Indonesia for funding my study and Integrated Laboratory for Advanced Material Characterization BRIN for all the material characterized here. And thank you. This is all my presentation.
Thank you very much, Ms. Christine. So wait first. Are there any questions?
It's quite interesting because I have similar research with you. My question is, what kind of polyvinyl alcohol do you use? As you know that, I don't know, you are aware or know that polyvinyl alcohol have different type. It depends on the degree of polymerization and degree of hydrolysis. So let's say if you are using type the partial hydrolysis of PVA or fully hydrolyzed of PVA, it will have different results. Just my question now, what kind of polyvinyl alcohol did you use in your research as your presentation?
Thank you. In this experiment, we use partially hydrolyzed PVA with molecular weight of 89,000.
Okay, partial. So it means the degree of hydrolysis is around 88 or below 88.
Yeah.
Thank you.
Yes, sir.
Thank you to Mr. Chairman for the opportunity. Okay, good presentation, Ms. Catherine, Ms. Christine, sorry. We'll look at the future of this battery, will lead us to the solid state battery, and of course, this solid electrolyte, again, important things that we need to improve. But the challenge that we face is the electrochemical performance kind of poor. The ionic conductivity is like below 10 power minus 6 or 10 power minus 5, but the industrial need we have to improve it to 10 power minus 4. So I kind of curious why you need we choose the PVA instead of other polymer hosts such as the PO because they have a record. It can lead us to higher ionic conductivity. And also, if you want to still use the PVA, so is there any chance for us to increase again the ionic conductivity numbers? Thank you.
Thank you for the question. Actually, for the PO, as we know that it is really wide known, and it's actually the first ones that being made into polymer, solid polymer electrolyte. But PO and compared to PVA, it has higher crystallinity, so we need more effort to lower its crystallinity. And the second one, the PO is not readily soluble if you want to make it a polymer blend because it is very, very selective in solvents. And in this case, we are making some effort to make some greener membrane. So as the first move, we want to make like the first easy solvent that we use every day, which is the ionized water instead of solvents like DMAC or NMP or DMF. So that is the first reason for us using PVA as the polymer host. And for improving the ionic conductivity, I think a lot of things that can be done, such as the first thing is of course the lowering the ionic crystallinity. One thing that we can do is using the filler. Using filler, either it's a active or inactive filler, or we can also use a plasticizer, or we can modify the polymer host so it is more friendly to the cation. Thank you.
Thank you.
Thank you for the questions and also the answer, Ms. Christine. So due to the limited time, we can move on to our next speaker.
Thank you.
So thank you for your time, Ms. Christine. Okay, so for the next speaker, I think it will be from Zoom. It is from University of Gajah Mada. So this Ms. Sutini, Mr. Tribayu, and Mr. Faru Rosi. So are you present?
Yes, I will present.
Okay, so Ms. Sutina. Okay, so you have 15 minutes. The time is yours.
Thank you.
Lalu dari
Okay, thank you for the time.
ditentukan juga dari komposisinya, dari bagaimana
Research
struktur
effect of pH on lithium extraction from diagram membrane using nanofiltration membrane. Okay, introduce for the lithium is have so many popular today, and then because of the batteries from lithium is popular, like the makeup for Tesla, and then for the batteries for like handphone, and then the lithium consumption in 2010 to 2025, we can look for the graph. In 2025, the lithium consumption prediction of 90,000 tons, and then for the lithium, we research we research from the proportion lithium in our extension in nature for the labs result of the LERS saltwater is the continental brine is the the biggest research in the world. But I focus on geothermal brands because in Indonesia have the ring of fire. They have so many volcano in Indonesia, so yes, the potential to get the lithium from geothermal brand. And then I using nanofiltration for my research because this nanofiltration from ion selective separation can application for the lithium extraction, lithium and then magnesium separation. My research for in Indonesia have three research about the lithium extraction. The first is from Sulistiono. They using precipitation to series alkalic acid and carbonate sodium, and then the second is from Lasari, the lithium extraction from brine water Tirta Sanita Bogor using evaporation method, and then the third is from Sutojo from lithium recovery from synthetic geothermal brine using electrodialysis method. So I use from my novelty from this research, I using nanofiltration membrane from extraction lithium from geothermal brine. From this research, I make a synthetic from geothermal brand from Dieng, Central Java, because in Dieng have some the lithium in Indonesia. So the component of the lithium in Dieng until 50 ppm. So I make the synthetic of the geothermal brand. And the first they have natrium chloride. They have 7,500 ppm. Calcium chloride 2,500 ppm. Magnesium chloride have 50 ppm. Calcium chloride has 400 ppm, and lithium chloride has 50 ppm. Then why I using nanofiltration? Because the nanofiltration is the very simple for this for the extraction lithium, and then the pore size is under 2.0 millimeters, and then they have a pressure drops 5 until 15 bars, and then it has the transportation mechanics from the first is size sieving, and then the second is Donan exclusion, and the third is the electric exclusion. And then the foundation of my theory, I searched about the permeate flux. Yes, it's the formula of the permeate flux. And then for the research methods, I make a synthetic from the geothermal brand from Dieng. Yeah, and then the tools I using that N modules for nanofiltration and membrane nanofiltration. This picture. Okay, this is the that N modules, and then this membrane nanofiltration membrane. This is procedure. Mix 25 grams of sodium chloride, and then 15 grams of potassium chloride, 0.535 magnesium chloride, 2.005 0.5 calcium chloride and 0.195 lithium chloride, and using distilled water and up to 1500 milliliters in beaker glass, and then test the pH of the initial solution for the experiment using three pH from acid, base, and neutral. And then the nanofiltration operation, put 100 milliliters of synthetic geothermal brine into the nanofiltration dead-end modules, after which nitrogen has applied to pressure to the module and accommodate the filtrate permeate and weight it. This the dead-end nanofiltration dead-end modules, the synthetic have put in the nanofiltration dead-end modules, and then we have operation of the nanofiltration. Then this is calculate the permeate weight every 5 minutes until the solution of the module runs of the well recording the time likely of the solution. For acids, the pH solution 3 until 4, and the alkali for pH 9 until 10. The treatment is the same for the neutral condition. This is the results and discussion. The Fermat flux, we can see at the pH 7 and pH 10, the process N is faster, and the Fermat flux value is also high, 5.05 and 8.5. Proportion of the solution of the inversely proportion to the solution at pH 3, and our solution is extract as a low permeate flux value at the number 3.5. And then in this nanofiltration membrane surface using SEMS, SEM vessel at pH 3, 7, and 10. The result of the SEM, we can see that the basic pH is a lot of residual solution trapped on the surface area of the membrane. It's in contrast with the pH 7 and 10. Only remain particle of the remaining solution are trapped on the surface of the membrane. This conclusion, the effect of the pH of lithium extraction from geothermal brine using nanofiltration membrane. First, it was found that pH 7 and 10 have the highest thermal flux value with value of 5.05 and 8.4, while in the pH 3 have the thermal flux has only 3.5, and then it can be concluded the more alkali solution as the faster lithium extraction process with nanofiltration membrane and the higher flux permeate value. And the surface area of the membrane also has a particle from the remaining solution. For analysis, for allotment, the research to express is credited for research technology Gajah Mada University Innovation, and then for LPDP for the my study funding. Okay, this reference. Thank you.
For presentation, I think we can open for one question. Is there any question from the audience or from the Zoom meeting? Okay, if there are no questions, we can move on to our next speaker. Thank you for the presentation, Ms. Sutina.
Thank you.
And also for the next presentation, from the oral contributor, there's from University of Indonesia, Miss Fiona, Ahmad Subhan, Prof. Ana Zulfia, and Alan Drew. And Prof. Alan Drew. Okay.
Yes.
Okay. So Miss Fiona,
Okay.
okay.
Thank
Please you can
Yes.
start your presentation. You have 15 minutes.
Okay, thank you. Okay, here I'm Fiona Angelina from Universitas Indonesia. I will present our research titled Characteristic of SN-doped and rice husk activated carbon-coated NMC811 as a lithium-ion battery cathode. Lithium-ion batteries are widely used as in electronic devices and electric vehicles because they have high power density and energy density, also less toxic and environmental friendly. One of its cathode materials is NMC811. This material has higher capacity, lower cost, less toxic, and more environmental friendly compared to other NMCs such as NMC622, NMC111, and so on. However, this material has drawbacks such as capacity fading, poor rate capability, and also thermal and structural instabilities. These drawbacks can be countered with modification by coating its surface or introducing a dopant into its structure. Here in our work, we modified NMC811 with thin doping and also coating with rice husk activated carbon. And for the methodology, first the rice husks were carbonized to get carbon, and then carbon was impregnated with sodium hydroxide and then activated to get the activated carbon. Here we name it as AC. And for the preparation of NMC811 and tin doped NMC811, we use the solution combustion method with nitrate precursor and glycine as the fuel. After the solution conversion, the powder we get was sintered to get the NMC811. Here we name it as NMC-SCS. And for the tin doped one, we name it as NMC-SN. And for the NMC811 coated rice husk activated carbon, the NMC-SCS that was prepared using the solution conversion were milled with activated carbon with the amount of 1 weight %, and then calcined to get the NMC coated rice husk activated carbon. Here we name it as NMC-AC. And then we conducted the electrochemical performance with the coin cell. Here we use PVDF, Super P, and NMC with the mass ratio of 1:128 with the NMC, that is NMC-SCS, NMC-SN, and NMC-AC. We mix these powders with NMP as the binder with the ratio 1:2 weight per volume. And then the black slurry, we coat it on aluminum foil with thickness of 150 microns. And then we assemble it to a coin cell. And for the result, here the rice husk activated carbon. Here is the spectra of Fourier transform infrared. The spectra shows no absorbance in AC sample due to the decomposition of volatile matter in carbon. Further, we characterize it with X-ray diffraction. Here, we get that the AC sample is semi-crystalline with theta 16 to 30 degree correspond to amorphous carbon, and 44.6 correspond to localized gravitization peak, and the 26 is the formation of a highly carbon cluster. This crystalline structure we get was due to sodium hydroxide activation at high temperature. And for the NMC-SCS, here's the reaction that took place when the solution conversion happening, and this is the de facto graph. We compared the NMC SES with the NMC 811 commercial. Here we name it as NMC Com. We can see that the two theta both have the same peaks at two theta. Here is and both are crystalline. Further, we characterize it with SEM. The right one is the NMC SES and the left one is NMC Com. We can see that both have a spherical shape with EDS similar with each other for the element nickel, manganese, cobalt, and oxygen. And for the NMC SN, NMC, and NMC AC, here's the reaction for the NMC SN that took place when the solution combustion synthesis. And this is the de facto gram shows that the modification did not affect the structure of NMC SES. And for the morphology, however, the left one is for the NMC SN, and the right one is the NMC AC. We can see that modification with SN making the morphology turn out to be irregular and bigger than compared to NMC SES and NMC AC. And for the EDS, the SN and C that were added, that both is 1%, is similar. And here is the electrochemical characterization using electrochemical impedance spectroscopy. We can see that the RCD for NMC AC is the lowest, and therefore the conductivity is the highest. So we can conclude it that the characteristic of NMC SES, NMC SN, and NMC AC were compared. The XRD pattern shows no significant difference. The morphology of NMC SES is similar to NMC commercial, that is spherical shape, and NMC SN showed a bigger agglomerated irregular particle, whereas NMC AC showed spherical shaped particles with several smaller particles. And for the electrochemical characterization, it showed that NMC AC gave the highest conductivity compared to NMC SES and NMC SN. And we would like to thank the Directorate of Research and Community Engagement for the PUTI Q1 grants. And here's the references we use. Thank you.
Thank you very much for your presentation, Ms. Fiona. Okay, are there any questions? Oh. Are there any questions? Okay.
Okay, thank you for the chairman. Maybe I want to ask one simple question that maybe I missed from your presentation, Ms. Fiona. You have mentioned about why you choose a activated carbon from the rice husk. Why you choose that kind of material, and can you give us some explanation by the view of the on the molecular side? What's the effect of adding the activated carbon to the composite, and why is it resulting higher ion conductivity? Thank you.
Okay. We choose rice husk because in Indonesia rice husk is we can easily find it, and also for the activated carbon from rice husk from literature I read, rice husk activated carbon has high specific surface area that is beneficial for the lithium movement in the battery. I'm sorry. What is the other question?
My question is actually the same. Why from the molecular aspect? What's the what can rice husk activated carbon bring to increase the performance? Why is it just that maybe?
The activated carbon, from what I know, it can enhance the it can enhance the conductivity of the battery. So we choose the activated carbon as a composite for the NMC 811.
Okay, thank you very much for your answer, Ms. Fiona, and for your presentation. We can move on to our next oral contributor. So we have from University of Indonesia, from PT Cakra Giri Energi Indonesia. No? Oh, okay. So, oh, okay. Okay, so now from University of Indonesia, Ms. Anissa, Ms. Christine, Mr. Muhammad Khalid, Mr. Hafid, and Mr. Adam. Miss, okay. Okay, so from Ms. Anissa, you have 15 minutes to present. The time is yours. The pointer.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good afternoon, ladies and gentlemen. My name is Anissa Hayarundati, and today I'm gonna present our recent research work with the title of a combined non-solvent and thermally induced phase separation, or NTIPS, method for preparation of highly porous cellulose acetate membrane as lithium-ion battery separator. So today's presentation will cover about its background, separator performance, and the conclusion. So let's talk about the background. We know that energy appears to be one of the most crucial issue in this year and within the coming years to obtain the sustainable development goals. So we need to the transition from non-renewable energy to renewable energy is highly recommended, and the role of energy storage system is also crucial because the renewable energy has to be stored in a suitable energy storage, and one of the energy storage system is lithium-ion battery. Why we talk about lithium-ion battery? Because lithium-ion battery is lightweight. Also, it has a high energy and power density. Basically, lithium-ion battery has four main components, which is anode, cathode, electrolyte, and separator. Separator doesn't undergo any electrochemical reaction, so it is considered to be an inactive component. However, it can affect the battery performance because it affects the battery cell kinetics. Why? Because in the separator, there will be the lithium-ion transport between those electrodes. So the sufficient and efficient ion diffusion between the two electrodes will affect the battery performance. There is a commercial separator in these days, but the separator has the sufficient mechanical strength, chemically stable, and electrochemically stable. However, it has a low porosity, wettability, and it is not sustainable materials because it is derived from fossil fuel. So we need a solution to overcome these problems. One of the solution is using biomass materials because the plentiful availability in this world, specifically in Indonesia. one of the biomass materials is cellulose acetate, and cellulose acetate is also abundant, and it is a low cost, also chemically and mechanically stable, and it has hydrophilic properties because of the presence of hydroxyl and carbonyl groups. The commercial separator has the other problem, which is low porosity and low wettability. So we need to overcome those problems by achieving a highly porous membrane. How? In this research, we recommend a method by combining nips and tips that will allow a pore formation without adding any pore forming agent or additives. The nips and tips will induce a phase separation by combining the non-solvent induced phase separation and thermally induced phase separation. So there will be an exchange between the solvent and the non-solvent. The overall process is shown in this figure. We use cellulose acetate as the polymer matrix and the NMP as the solvent. When we blend the polymer and the solvent, we will get the polymer solution. The stirring process to get the polymer solution is in 70 degrees, and then the polymer solution will be cast in a glass plate. So we will leave it so it can be evaporated, and the evaporation times is varied at 55 minutes, 65 minutes, and 75 minutes. And then after the evaporation time, we will immerse the polymer membrane to the coagulation bath as the non-solvent. So why we need to vary the evaporation time? The evaporation time will relate to the polymer fraction. The shorter the evaporation time, the polymer fraction will be low as well, because there will be still more remaining solvent. And then when we increase the time for evaporation time, there will be a higher polymer fraction. Why we need to maintain the polymer fraction? Because when we quench the polymer into the coagulation bath, there will be a difference in its pore structure. If it's in the lower polymer fraction, there will be a phase separation. The polymer solution will separate into two phase, polymer rich phase and polymer poor phase. But we need to remember that when we lower the polymer fraction, it has to be higher than the critical point, because if it's lower than the critical point, the membrane won't be formed. But if the polymer fraction is too high, it won't be separated as polymer rich and polymer poor phase, so there won't be any porous structure, and and that will happen is solid liquid separation. So we need to maintain the polymer fraction by maintaining the evaporation time. From our research, we also observe and analyze its performance. First, we need to validate the cellulose acetate as separator. Cellulose acetate has few absorption characteristics, such as carbonyl group, methylene bending, CO bond stretching, and OH bond absorption. The thing that we have to note is cellulose acetate has polarity because of its polar groups such as carbonyl group and hydroxyl group. So it can form a hydrogen bond. This hydrogen bond will influence the cellulose acetate performance on its hydrophilicity and electrolytic properties, so it can be weighted more easily. The porosity of the foam membrane, the result is the shorter the evaporation time, the higher the porosity. Why? Because when the evaporation time is 55 minutes, there will be a high exchange rate because there is still much more remaining solvent than the 75 minutes. If the remaining solvent is still high, so there will be a liquid-liquid demixing, and the microporous structure will be produced. We also observe the SAM image, and we know that the top section or the surface morphology represent as evenly distributed pore structure, and it has the pore size diameter average is 1.17 micrometer, which is suitable for battery separator because the requirement is around 1 micrometer for lithium-ion battery separator. And then the electrolyte wettability. This is also related to the porosity. The 55 minutes of evaporation has the highest porosity because of the porous structure can increase the weighting rate and compatibility between membrane and electrolyte. We also observe after dropping the electrolyte 3 seconds and 30 seconds. We know that the weighting rate is quite high because there is a change in the contact angle. And then the electrolyte uptake, it also related to the porosity. The 55-minute evaporation time show the highest electrolyte uptake. This is also because of the polar groups that affect the electrolyte interaction, and there also be an interaction with electrolyte through Coulombic interaction. The thermal shrinkage is also related to the porosity. The 55-minute membrane has the greatest shrinkage. This is because heating will cause densification and pore constriction. So that membrane will have the greatest shrinkage. And then the mechanical properties, the porosity is also related because membrane with highest porous will have a more air-filled pore space, so there will be less material to withstand the load, so it will have the lowest mechanical properties. In this term is the tensile strength. We also observe the bending, and then the rolling, and then the folding to observe its mechanical properties to using physical method. And the last thing we observe is the ionic conductivity. This ionic conductivity is contributes to the porous structure that allows ion to conduct between the electrode. This is also related with the high electrolyte uptake and well-connected pores that we have seen in the SAM image. From this research, we have concluded that the produced membrane has the higher ionic conductivity than the cell guard or the commercial separator. The conclusion is N-tips has successfully produced a highly porous structure of cellulose acetate membrane, and the less evaporation time will have more remaining solvent, so it will have a higher exchange rate and higher porosity. High porosity will result in high electrolyte wettability, electrolyte uptake, and high ionic conductivity. However, the thermal shrinkage and mechanical properties will be lower than the more evaporation time, but it is still acceptable to be lithium-ion battery separator requirement. Thank you. That will be all.
Okay, thank you very much for the presentation. Are there any questions from the audience? No? From the Zoom meeting? Oh, no. Okay. Okay, so I think there are no questions. Oh, no, okay, sorry.
Thank you for your presentation. It is interesting for me because it's also similar with my research. But I want to ask you what electrolyte you use because in my research, cellulosa acetate need modification because it dissolved in electrolyte. But I use electrolyte is lithium phosphate, LiPF6, LiPF6. So what the electrolyte you use, and did you need do you need modification for your membrane?
We use lithium perchlorate or LiClO4 as the electrolyte, but you have to remember we need to control the moisture because it might affect the dissolve between the cellulose acetate and the electrolyte.
So for your membrane did not dissolve at all.
From the ionic conductivity result, the membrane hasn't dissolved.
Thank you.
Okay, are there any other questions? Okay, so thank you very much for your presentation. And now we move on to our next oral contributors. It's from the University of North Sumatra. I think it will be from the Zoom meeting. Ms. Diva, Mr. Syahrul, Mr. Nurdin, and Mr. Dolly. Are you present?
Okay, sir. Wait a minute. I will prepare my presentation.
Okay. Okay, so you have 15 minutes to present. The time is yours.
Okay.
I have presenting view,
Okay.
the slideshow view.
Okay. Can you see my slide?
Yes, but it's in PowerPoint. Maybe you can start the slideshow. You can start your presentation.
Okay, thank you very much. First of all, actually our research has been updating in the new rearranged title, with the title effect of oil palm fiber on physical and physiological behavior of unsaturated polyester oil palm as composite. This research was conducted by Iva Almira, Syarul Maidi, Nurdin Siregar, and me, Doli Monardo. We are from Universitas Sumatera Utara and Universitas Negeri Medan in the Medan City, North Sumatera, Indonesia. Okay, as we know, the development of composite technology has progressed very rapidly in recent years. Because of composite materials have the advantage of being renewable, so that they have good strength against high loads, stiffness, and resistance to corrosion. Polymer composite, especially, have been extensively modified to produce superior product and to maximize their usability. Specifically, polymer composite based on polyester resins with are often used as raw materials for mechanical applications such as brick pads, fluid pad, or even vehicle propulsion systems. This is not without creation because polyester resin-based polymer have mechanical and physical properties. However, polymer composite in general can be applied to various fields according to the main properties that are known dominant. Various attempts have been made by researchers around the world to maximize the function of polymer composites, such as improving one or more of their physical properties, to finding new ways to create alternative materials to replace some of the composite components. This method in detail can work by carrying out special treatment in order to get the expected advantage. One of the polymer composite technology that is developing and attracting the attention of researchers in the world today is fiber reinforced polymer composite or NFCs. Some of its superior properties, such as high modulus and good strength, are the main reasons why these materials play an important role in various applications. In addition, with the aim of reducing the carbon footprint on the environment, the fiber reinforcement commonly used is sourced from nature so that it does not contribute to increasing environmental damage. This has prompted researchers to focus on natural fibers such as henna, oil palm fiber, jute, rice husk, bamboo, banana, and etc. as a polymer composite reinforcement material. Because these materials are environmental friendly and have proven to be reliable polymer matrix reinforcement, resulting in composites that are low in cost and also easy to fabricate. History record that natural fibers are usually used in various applications on a host scale, such as clothing and household textiles. However, now natural fibers have been widely used as the main reinforcement in various types of composite materials, especially in polymer composite, compared to the use of conventional fibers such as glass fiber and carbon fiber to obtain thermoplastic polymer composite. Some of the other unique properties of NFCs are non-conductive, which is very difficult for electrons to move within their structure due to the weak electronic structure of NFCs. So this material is a good insulator. One of the natural fiber that has gained a place for researchers in the world because of its very superior properties is oil palm fiber. This material is obtained by extracting the empty fruit bunch of oil palm through the rating process. There are several rating processes, such as mechanical rating, chemical rating, and then steam rating and also water rating. A popular technique is water rating. Fibers have a porous fiber surface morphology, so they are very useful in improving mechanical properties when joining polymer matrix because of their mechanical interlocking ability. Furthermore, OPF or oil palm fiber has a relatively low density of 0.7 to 0.9 gram per centimeter cubic, tensile strength of 50 to 400 megapascal, and Young's modulus of 0.57 to 9 gigapascal. Apart from OPA, oil palm ash or OPA is also been popular as a filler in polymer composition. And OPA is a waste product of the oil palm fluid. So, in this present work, we focus on investigating the physical and physiological behavior of unsaturated polyester oil palm as composite incorporated into oil palm fiber through a simple hand layup technique. Now we are going to the method. First of all, we have to prepare the raw material of this research. Oil palm ash or OPA and oil palm fiber or OPF were obtained from Lonsum Bagarpang Plantation, Tanjung Morawa, Deli Serdang Regency, North Sumatra, Indonesia. The epoxy resin was supplied from LSC Tosin, Indonesia. Methyl ethyl ketone was supplied by Redox Chemical Australia, and other materials are supplied from local North Sumatra companies with analytical and technical grade. First, oil palm fiber was washed thoroughly and cut into small pieces with random orientations along 1 cm or 1 centimeter. Then dried in the sun for 1 night. The fiber were then soaked in 5% of sodium hydroxide solution in a water bed for 2 hours, and then rinsed in fresh water to neutralize the effect of NaOH and dry material from temperature. For preparation of composite, polyester and NPKP with a ratio of 100 to 1 patient to hardener were mixed in a container and stirred manually for 1 hour at room temperature until the resin solution was mixed. Next, OPA or OPA is added to the matrix by manual stirring to improve the bonding characteristic of the fiber. Oil palm fiber at 0, 5, 10, 15, and 20 weight percent loading was properly mixed with polyester matrix by using a hand stirrer and gradually poured into the wooden mold of a dimension 300 millimeters, 300 millimeters, and 2 millimeters. Sorry, 10 millimeters. METP is used as a hardener in the manufacture of lead, and oil palm as is used as a carrying accelerator cross-link catalyst for unsaturated polyester resins. The hand layup technique for 24 hours with a nominal pressure of 2.5 megapascal at normal room temperature. And the design and composition of each sample as well as prepared sample, yeah, like in this table. And now we are going to result and discussion. First is the density and porosity. It can be seen that the highest density value is found in the EAF10 sample with a value of 1.3 gram per centimeter cubic, and the lowest is owned by EAF20 sample, which the value is 1.2 gram per centimeter cubic. OPF, one more, is a porous morphological structure so that it has a like enough facial space. It is this factor that becomes possible that causes the density of the composite to increase when the mass concentration of OPA reaches 10 weight of percent. Porosity values actually show an inverse relation with density. This is consistent with the fact that the higher the sample density, the lower the porosity value as a result of single the overall volume of the sample. This sink rates can be caused by several factors related to the operation of OPF as a composite reinforcement. In addition, the main factor that almost influence is because OPF helps increase the bond strength between matrix particle in polymer, will be supporting the compacting process between the matrix and the pillar of the cross-linking region.
Our time is 2 minutes left.
Okay. And then the water observation. The water observation of the specimen was calculated as follow equation. Yeah. And the result is so that the OPF add polyester OPA composite is having marginally higher resistance to water absorption compared to the other sample. But when the OPF reach to 20% weight percent, actually increase the water absorption again. This might be due to characteristic of the vessel in OPF, which will actually increase the capillarity in the structure. And then the coefficient of friction and wear rate. The coefficient of friction and the sample wear and the wear rate calculated using this equation. And the result, the performance of 10% weight OPFS reinforced polyester composites of a low wear rate compared to all other specimens. And this performance was remarkable at higher plate load condition. And with the increasing of plate load, the coefficient of friction for all samples showed increasing trend, and notably the maximum friction coefficient was observed at the highest of plate load of 39.24 Newton, with increase in the plate load and increase in the friction coefficient were observed at 1 more 10% of weight percent of fiber reinforced composite. So from our research, we conclude that as we know, OPF has a cross morphologist, so that it has less enough vessel space. OPF concentration more than that will cause a sinking of the matrix mass, which result in a decrease in density. In addition, the addition of OPF up to 20% mass concentration will also increase its water absorption because of its vessel in OPS structure. The lost Hall particle and agglomeration were first detected during the wear test, and the presence of such particle was predominant in 10 weight of percent of fiber reinforced composite compared to 0 and 5 weight of percent fiber reinforced composite. Okay, maybe just that what I can deliver to you about our research. Thank you.
For your presentation. Maybe due to the limited time, we cannot have any questions, and we will move on to our next speaker. So thank you, Mr. Wali.
Okay, thank you.
Okay. Okay, so for the next speaker, we have from University of Indonesia, Mr. Justinus, Prof. Anne, and Prof. Evi. So, okay, so are there any representative present?
Yes, I am the representative of Mr. Justinus Purwamarga Pratala.
Oh, okay, okay. So you have 15 minutes to present. Please take your time.
Okay, thank you for the time and for the opportunity given to me. Good afternoon, ladies and gentlemen. My name is John Zamir Zidan. Today, I will present our work about synthesis and characterizations of Musa paradisiaca formatypica banana peel derived carbon quantum dots. This is the table of content of this presentation. There is an introduction, experimental, result, and discussion, then conclusion. Carbon quantum dots, or known as CQDS, is a new type of zero-dimensional carbon nanomaterial with size less than 10 nanometer, which has potential as an additive for lithium-ion battery material because the nature of carbon quantum dot that can increase conductivity value of lithium-ion battery material. This is the nature of carbon quantum dots. It has good water solubility, good chemical stability, non-toxic for environmental, semiconductor, and good conductivity. Many precursors have been chosen to synthesize carbon quantum dots with a chemical and physical approach, but still, green technologies for synthesizing carbon quantum dots are gaining more importance due to their environmentally benign approach. Most of the previous research synthesized carbon quantum dot by bottom-up process. As you know, Indonesia has many species of plants, some of which produce biomass that can be used anymore and just thrown away. Musa paradisiaca formatypica, also known as pisang kepok banana peel, is chosen because it has the potential for becoming a raw material to synthesize carbon quantum dots. It contains 60% of cellulose, and this cellulose can be used as a carbon source to synthesize carbon quantum dots. The second one is experimental. In our, this is the same how we synthesize carbon quantum dots. The first one, we cut small the material by smoothing using a blender, and in this process, we add aquabides as a solvent. Then the solution was put in the autoclave for hydrothermal process for 4 hours and 180 degrees Celsius. The solution was obtained with brownish color. Then, as a qualitative testing, we fired the solution with UV rays 365 nanometer wavelength and produced a cyan color. The synthesis of carbon quantum dots with the hydrothermal process will be characterized by UV spectrophotometer to find out the wavelength and absorbance while analyzing its crystal structures using the X-ray diffractometer to analyze crystal morphology of the synthesized carbon quantum dots using the scanning electron microscope, and sample conductivity will be measured by using LCR. We come to result and discussions. This is the result of XRD analysis of obtained peak at concentration of 40% is 2 theta equal to 15.04 degrees. At concentration of 50% is 2 theta equal to 21.56 degrees, while at concentration of 12.5% have detected a peak to theta equal to 21.29 degrees. And the last one is at concentration 2.5% observed peak 2 theta equal to 21.5 degrees. It is also detected the lattice plane 002 and showed the amorphous character of the sample material. Based on reference from previous studies, carbon quantum dots derived from coffee grounds have a peak at 2 theta equal to 24 degrees, and carbon quantum dots derived from sugar have a peak at 2 theta equal to 21.21 degrees. This is a qualitative testing of solutions that contain carbon quantum dots by firing UV rays with 365 nanometer wavelength. Figure A shows solutions under visible light, and figure B shows the solution under UV light. This is an SEM analysis of the sample, and this is the ADS scan for the sample, for each sample. It shows that more than 50% of component is dominated by carbon when analyzed on E equal to 0.277 kilo electron volt. The next one is analysis of the UV spectrophotometer, it shows the absorbance that the sample has. The greater the concentrations of the sample the greater the absorbance it has. In addition, the treatment of time and temperature influence as shown by figure B. The next one is the result of LCR testing of banana skin samples that have gone through the hydrothermal stage, and raw banana skin samples are shown in chart A. In the graph of the result of regency effect on vulnerable 42 haze to 1 mega haze in the sample, it can be seen that there is difference in graph and calculation results where samples that have gone through the hydrothermal stage have higher conductivity than the raw samples. The higher concentrations of hydrothermal samples, then the higher the conductivity it also has, as shown in chart B. So we come to the conclusions. It has synthesized carbon quantum dots with biomass Musa paradisiaca formatypica, banana peel with hydrothermal process approach at 188 degrees Celsius for 4 hours, resulting in cyan or greenish blue colored flaring when illuminated with UV rays with wavelength of 365 nanometer. XRD analysis shows the amorphous shape with the peak at 2 theta equal to 20.56 degrees. Result of the UV spectrophotometer test can show that the higher the concentration of the samples, the higher the absorbance ability of the samples. And the result of the LCR test also indicate that there is an increase in the conductivity ability of the sample that has gone through the hydrothermal stage compared to raw samples. Due to its semiconductor and nature of carbon quantum dots, in subsequent research, carbon quantum dots will be applied to the LIB materials. This is the reference we use in this work. I think that's all. Thank you for the time and for the opportunity. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Okay, thank you very much for the presentation, Mr. Shan. Are there any questions from the audience or from the Zoom meetings participants now? Okay, so I think there's a question from the Zoom meeting participant. You can open your mic.
Okay, thank you. Let me introduce. My name is Boy, and I have been research about carbon quantum dots, and I have one question for you. How does your proof that your carbon quantum dots is it real within particle size less than 10 nanometer? Because I don't see about the proof about the particle size that make sure that is a carbon quantum dot. Thank you.
Okay, thank you for the question. So you asking for the proofs of carbon quantum dots that has been synthesized by us. For the introduction, this paper is a preliminary research, so we just work to prove that this material can indicates or shown carbon quantum dots by a qualitative testing. So in the subsequent research, we will prove or work more about the application of this material and the testing of the characterization you mentioned. Is that enough answering your question?
Okay, sir. Thank you.
With all pleasure.
Okay, thank you for the question and answer. Are there any other question from the Zoom meeting participant? Okay, thank you very much for the presentation, Mr. Swan. We move on to our next oral contributors.
Thank you. Thank you.
That's all for the oral contributions today. Thank you for all the presenters and the keynote speakers and invited speakers. And I would like also to thank our gold sponsors, Thermo Fisher Scientific, Factor, Trendsetter, and also LSP Kimia Industry, and also our partner, Asosiasi Penambang Nikel Indonesia, APNI, for this event, and also for the training of trainers. I think that's all. I'll give back to the MC.
Yeah, thank you, Mr. Distinguished Chairman, for your time. I think it's really an insightful session, and also for invited speakers and our contributors. Thank you so much for having the time with us, for sharing your knowledge and also your work. Hopefully, we can maybe give a contributor to the next technologies for advanced and also material technologies. But before we end the session, we will have a certificate of appreciation. And for Mr. Adi Tribiguna, of course, and we'll be hand over with Mr. Baihaki Muhammad, please. Yeah, on behalf of the committee, we would like to give a certificate of appreciation to Mr. Adi Tribiguna as our distinguished keynote chairman for today's afternoon keynote session. Okay, thank you so much, Mr. Adit. And I think that's all, ladies and gentlemen, who comes in person, also in online. This is our end of session, and see you tomorrow at 9 a.m. Thank you. Bye-bye.